There is a moment, a precise, mathematical moment. A moment so thin, it has no thickness at all. And the instant you cross it, the future stops being in front of you. It moves downward. The future is no longer a direction in time. It becomes a direction in space, a physical location, something you are falling toward, whether you want to or not. Physicists have known about this for decades. It is written cleanly into Einstein's equations. It is not a metaphor. It is not a thought experiment. It is geometry. And it means that inside a black hole, time and space swap places. The thing you thought was time becomes space. The thing you thought was space becomes time. And what that actually means, for physics, for reality, for the question of whether the future already exists, is something that almost nobody has stopped to think through to its conclusion. Until now. To understand what happens inside a black hole, you first need to understand what time actually is. Not philosophically, physically. In Einstein's universe, time is not a clock ticking in the background. Time is a dimension. Just like left, right, forward, back, up, down, time is a direction you move through. And just like the other three dimensions, time can be stretched, compressed, bent, and warped by mass and gravity. Near an ordinary star, time ticks slightly slower than in empty space. We measure this. GPS satellites have to correct for it, or they drift by kilometers every day. Near a neutron star, time slows further. Near the surface of a black hole, time slows so drastically that from the outside, a falling object appears to freeze completely. It never seems to cross the edge. It just hangs there, redder, dimmer, forever. But that is only what the outside observer sees. For the person falling in, something completely different happens. From the perspective of someone crossing the event horizon, they feel nothing. No wall, no alarm, no flash of light. The edge is invisible. You cross it without knowing, but the moment you do, the equations change. Before the horizon, in normal space, you have freedom of movement. You can go left or right, forward or back. You can choose your direction through space. Time, however, flows only one way. You cannot go back in time. You can only move forward through it. That asymmetry, free space, locked time, is what we experience as reality. But inside the event horizon, that asymmetry reverses. Space becomes locked. Every direction in space now points toward the singularity. You cannot turn away from it, any more than you can turn away from tomorrow. And time becomes free. It spreads in multiple directions. Past and future become spatial concepts. The singularity is not in your future the way death is in your future. The singularity is below you the way the floor is below you. Inescapable. Not because of destiny, but because of geometry. Here is what that actually means if you fall into a black hole and somehow survive. You are falling, accelerating. The singularity is beneath you the way the ground is beneath a falling elevator. And time, the dimension you once moved through helplessly in one direction, is now something you have partial freedom over. You could, in theory, move through time in different ways. The equations allow it. But moving through time now costs you spatial distance. Every second you try to stall, you move closer to the center. You cannot hover. You cannot pause. Inside a black hole, standing still in time is physically impossible. The price of staying in one moment is moving through space. and all of space leads to the same place. This is not poetry. Physicists can write the exact numbers. The Schwarzschild metric, the equation describing space-time around a black hole, has a minus sign that flips at the event horizon. That single sign change is what swaps time and space. One minus sign, and reality becomes a different thing entirely. But here is the part that nobody talks about. If time becomes a spatial direction inside a black hole, then both directions of time exist simultaneously inside that space. Not just the future, the past too. Outside a black hole, you can only move forward in time. Inside, the equations describe a space where both temporal directions are real spatial locations. Some physicists interpret this as meaning that inside a black hole, the past still exists as a physical place, not as a memory, not as a record, as actual present geometry. The Big Bang, the first moment of the universe, is not just a memory inside a black hole. It may be a spatial location you could theoretically point toward, an address, a direction. This is what general relativity says. Whether it is real, whether matter could survive to experience it, whether quantum mechanics changes the answer, those are open questions. But the mathematics is there, clean, unambiguous, and it has been since 1916. Now bring in quantum mechanics, and things get stranger. In quantum mechanics, time is not a dimension you inhabit. Time is a parameter, a number fed into equations that tells particles how to evolve. And quantum mechanics has a deeply uncomfortable relationship with time reversal. Most quantum equations are symmetric in time. Run them forward or backward, you get the same result. A particle moving from A to B and a particle moving from B to A are described by the exact same mathematics. Quantum mechanics does not have a built-in preference for the future over the past. The arrow of time, the reason yesterday is fixed and tomorrow is open, is not in the fundamental equations. It emerges from statistics, from entropy, from the overwhelming probability that large systems move from ordered to disordered states. But at the fundamental level, at the level of individual particles and fields, the equations do not care which direction time flows. They treat past and future as equivalent. And inside a black hole, where time has become a spatial direction, that quantum symmetry becomes geometrically real. In 1974, Jacob Bekenstein and then Stephen Hawking made a discovery that connected black holes to thermodynamics in a way nobody expected. Black holes have temperature. They have entropy. They obey the same laws as steam engines and refrigerators. And the thing that gives a black hole its temperature, Hawking radiation, is a quantum effect that lives at the event horizon. Pairs of particles spontaneously appear near the edge. One falls in, one escapes. The black hole slowly loses energy. But what nobody fully resolved, and what physicists are still fighting about today, is what happens to the information inside. The quantum state of every particle that ever fell in. Quantum mechanics says information cannot be destroyed, but Hawking's original calculations said it was. That contradiction, the black hole information paradox, is one of the deepest unsolved problems in physics, and it connects directly to the question of time. Because if information is not destroyed, if everything that fell in is somehow preserved, then the interior of a black hole is not a place where the past disappears. It is a place where the past is locked, encoded, geometrically frozen. A library written in space-time itself. In the 1990s, physicists Leonard Susskind and Gerard 't Hooft proposed something that sounds impossible. All the information inside a black hole, everything about every particle, every quantum state, Every piece of history that ever fell through the horizon is encoded on the surface of the event horizon. Not inside, on the surface. A two-dimensional shell containing the complete description of a three-dimensional interior. This is called the holographic principle, and it led to one of the most powerful ideas in modern physics, the ADS/CFT correspondence, which suggests that the interior of any volume of space is completely equivalent to the physics on its boundary. The inside of the universe is a hologram. The three dimensions you move through might be a projection from a two-dimensional surface you will never reach. This is not metaphor. Physicists use ADS/CFT to solve real equations. It produces real, verified results. And what it says about time is extraordinary. Time, in this framework, is not fundamental. It emerges from the structure of information on the boundary. Time is what it feels like to process information, and inside a black hole, where that processing reaches a limit, time does not end. It transforms. In 2014, Carlo Rovelli and Francesca Vidotto published a paper proposing that black holes do not end at singularities. They bounce. Loop quantum gravity, a theory that treats space itself as made of discrete, indivisible chunks, predicts that you cannot compress space beyond a certain limit, the Planck length, 10 to the power of -35 meters. Beyond that, space pushes back. The collapse stops. And in a quantum bounce, the arrow of time reverses. The singularity that was your inescapable future becomes your past. The geometry that was pulling you in begins pushing you out. You pass through the Planck regime, the place where quantum gravity dominates and our equations give up, and emerge into a new geometry. Some physicists call what emerges a white hole, an object that only expels, that only pushes matter outward. That is a black hole with its time direction reversed. And if Rovelli is right, every black hole in the universe is a future white hole waiting to happen. The clock inside is ticking, toward a bounce, toward a moment when time, even inside that locked and falling geometry, turns itself around. There is a symmetry in physics called CPT symmetry. C stands for charge. Flip every particle to its antiparticle. P stands for parity. Mirror the universe left to right. T stands for time. Run everything backward. The deep laws of physics are believed to be invariant under CPT combined, meaning if you took the entire universe, switched every particle to its antiparticle, mirrored it in space, and ran time backward, you would get something indistinguishable from the original. This means time reversal is always possible in principle. It is statistics, entropy, that makes it feel impossible in practice. Inside a black hole, where entropy is not increasing in the ordinary sense, where the thermodynamic rules behave strangely, time reversal is not just a thought experiment. It is a live possibility in the equations. Some physicists have proposed that the interior of a black hole is a CPT mirror of normal space. That an observer falling in experiences time flowing forward toward the singularity, while another observer in the CPT mirror experiences time flowing backward, from singularity to horizon. Two observers, same black hole, opposite arrows of time. Both valid, both described by the same mathematics. The James Webb Space Telescope has been doing something that connects to all of this in a way that is deeply unsettling. It has been looking at the earliest galaxies in the universe, objects formed just a few 100 million years after the Big Bang. And what it is finding defies our models. Galaxies that are too massive, too structured, too chemically evolved. Things that should not exist yet, but do. Our standard model of cosmic structure formation says the universe needed billions of years to build such complex objects. Webb is finding them almost immediately. There are several explanations being proposed, but one, quiet, published, not yet ruled out, connects directly to everything we have discussed. If time inside collapsed objects does not behave like time outside, if there are regions of space-time where entropy runs differently, where structure can form faster because the causal rules are not the same, then the early universe might not have been as empty and simple as we assumed. It might have inherited structure from something that came before, from geometries where time ran in directions we do not experience here, from a universe where the past was also the future, and the future was already built. We have now detected hundreds of gravitational wave signals, collisions between black holes, mergers of neutron stars. Each one sends a ripple through the fabric of space-time itself, a wave that travels at the speed of light across billions of light years and arrives here as a distortion smaller than 1,000th the width of a proton. We measure it. We reconstruct the masses, the spins, the distances, the orientations of objects that collided before our solar system existed. And in every one of those measurements, Einstein's equations pass the test. They predict the signal exactly. But there is something we do not yet measure. What happens at the moment of maximum compression? The instant the two objects merge into one. The moment the singularity forms, or does not form, if quantum gravity intervenes. That moment is hidden inside gravitational waves so high in frequency that our detectors cannot yet resolve them. The next generation of detectors, already in development, may reach that frequency range. And what they find there, whether it is a clean singularity or a quantum bounce or something stranger, will tell us what time does at the extreme limit. At the edge of the floor that falling geometry creates, at the moment when space runs out. Here is the conclusion that follows from all of this. We think of time as the one thing that moves in only one direction, the thing we cannot reverse, cannot slow, cannot escape. We built all of our intuitions about reality around that assumption. Past is fixed, future is open. The arrow only points one way. But the physics says something different. Time is a dimension, and like all dimensions, it can be curved, warped, and, at the extreme limit, flipped. Inside a black hole, what was your future becomes your floor. What was your past might still exist as a spatial address. And at the quantum level, past and future are treated as equivalent by the fundamental equations. The only reason time has an arrow is entropy, the overwhelming statistical tendency of large systems to disorder. But entropy is not fundamental. It is emergent. It arises from initial conditions. And if the initial conditions were different, if you were inside a black hole, approaching a Planck scale bounce, falling through a geometry where entropy rules no longer hold, then the arrow of time is not a law of the universe. It is a feature of where you are standing. Right now, somewhere in the universe, a black hole that swallowed its last meal billions of years ago is approaching its bounce. The singularity is not ending. It is turning inside out. Time is not stopping. It is redirecting. And whatever emerges from the other side will not know that it came from a death. It will only know that it is moving forward, into a future that, from where we stand, is already the past.